Hello.
Hello. So
Hello.
please, yeah.
Yes, sir.
So I'm audible now.
Yes, sir. You're audible and your lecture is
You
also
you you can respond in the chat box. Okay. Please mute yours.
okay.
Thank you. So good afternoon, everyone. I am Keshav. I am currently research scholar at IIT Kanpur. So I am taking this problem solving session of week 8 NPTEL course ME111, which is applied numerical method. So before starting this problem solving session, let us recap whatever we have discussed till week 7. So in week 1, we have discussed what are the numerical methods and why it is important. There we have seen some root finding methods where we have some fx equal to 0, which may be non-linear or linear function. So we are trying to find out this root of this fx equal to 0. Okay. So there we have discussed two methods. First method is bisection method and second method was Newton-Raphson method. Then in week 2, then in week 2, we have discussed about basics of programming in Python. There we have seen basic array operation in my Python and elementary mathematical operations. In week 3, from here we have came to the linear algebra part. So in linear algebra part, there can be two type of problems. One type of problem is ax equal to b type of problem. This is system of linear equation. And another type of problem that can be discussed is ax is equal to lambda x type of problem, that is eigenvalue problem. So in week 3, we have discussed solution of system of linear equations. There we have discussed Gauss elimination method, which is a type of direct solver. There we have seen effect of partial pivoting also. Then in week 4, first part of week 4 contains solution of system of linear and non-linear equations, where we have discussed LU decomposition method and some iterative solvers like Jacobi iteration and Gauss-Seidel iteration. There we have also seen the condition for Gauss-Seidel and Jacobi iteration to converge. Then we have seen system of non-linear equation, how to solve a system of non-linear equation. There we have applied this Newton-Raphson method to convert a system of non-linear equation into a series of system of linear equation. Then that series of system of linear equation can be solved using any linear solver like direct solver, Gauss elimination, or LU decomposition method, or we can solve using iterative solver like Jacobian and Gauss-Seidel. Then we have moved towards the eigenvalue problem, ax equal to lambda x type of problem. Then there we have seen how we can find, suppose we have a square matrix A, then how we can find all eigenvalues and all eigenvectors. So by using the power method, we can find out the absolute maximum eigenvalue and its corresponding eigenvector. Once we have found out absolute eigenvalue and absolute eigenvector, maximum eigenvalue and its corresponding eigenvector, we can use inverse power method to find out the absolute minimum eigenvalue and its corresponding eigenvector. Then by using the shifting method, we can find other eigenvalues and its eigenvector. Then by week 4, we have covered the linear algebra part. Then we have moved towards the calculus part. So the main difference in numerical method is here we know function values at discrete point only. So whatever we have discussed before this course, there the function was either continuous or piecewise continuous. So here we have function value only, or we wish to find the function value at only discrete point. So the first thing that we have discussed is the interpolation. So interpolation means we have the function value at some discrete point. Then we try to find out a polynomial that can exactly fit at the given discrete point. There we have discussed we have discussed the van der Waals matrix method. This method is very tedious. That's why we have discussed some method that are computationally less extensive, which are Newton interpolating polynomial method and Lagrange interpolating polynomial method. Then we have in week 5 only we have seen finite difference method. What is finite difference method and what is its use? Then in week 6 we have discussed numerical integration. So in numerical integration, what we do? First we fit a interpolating polynomial. Then we integrate it. Then after that we integrate it. Okay. There we have seen trapezoidal rule, Simpson's 1/3 rule, and Simpson 3/8 rule. We have also seen how to do a double integration. Double integration is nothing but a series of single integration. Okay. Then in last week, means the week 7, we have discussed how we can solve numerically ordinary differential equation. This ordinary differential equation can be of two types. First can be this initial value problems, means what we have some ordinary differential equation. Suppose we have some function of u prime, u double prime, x equal to some equal to 0, suppose. So, and we have three boundary conditions, three initial conditions. Suppose u at x equal to 0 something, and u prime at x equal to 0 equal to something a and b. If we have this is kind of initial value problem. So this initial value problem can be solved by using the Euler method. Euler method is first order accurate. That's why we have discussed some higher order accurate solvers, that is Runge-Kutta method. So Euler method can be inferred as a first order Runge-Kutta method. There we have seen the most commonly used fourth order Runge-Kutta method to solve a initial value problem. Then we move towards the boundary value problem. So boundary value problems are second order ODEs or higher order ODEs. So this can be solved. These boundary value problems can be solved using shooting method. In shooting method, we just convert this boundary value problem into a initial value problem. Then this, by using the shooting method, we solve this. Or we can directly solve this boundary value problem using finite difference method. There we convert the ordinary differential equation into a system of linear equation. Then this system of linear equation can be solved by the linear solvers like Gauss-Seidel iteration, Jacobi iteration, or direct solvers like Gauss elimination or LU decomposition. Okay. So by this, we move towards week 8, that is this week. So in this week, we are going to discuss the numerical solution of partial differential equation. So let us first recap what is partial differential equation? So whenever we have more than one independent variable, then partial differential equation comes into picture. If I write in general form first order partial differential equation, then it will be some function f that will be the function of u dependent variable, x, y that are independent variable, and is partial derivative, where u is a function of independent variable x and y. So in general, first order PDEs can be written as this. Okay. Now, if I write second order PDEs, so this second order PDE will contain u, x, y independent variable, first derivative of u with respect to x, first derivative of u with respect to y, then second derivative of u with respect to x, and second derivative of u with respect to y, then its cross derivative. So in general, second order PDE can be represented as this. This PDE, when u is a function of x and y, two variable. Okay. In general, u with independent variable x and y, nth order PDEs can be represented like this. Phi. So in short form, we write del u upon del x equal to u subscript x. Similarly, if I want to write u del 2u del x del y, that will be equal to u x y. Okay. But in general, u can be function of not only two independent variable. It can be a function of m independent variable x1, x2, x3, or xm. Okay. But in this course, we will see only second order PDEs with at max 4 independent variables. That is time plus 3 space coordinate. Okay. So the PD f of u equal to g of x of y. In general, PDs can be written like that. And this f in general can be written as if it is a second order PD equal to a uxx plus b uxy plus c uyy plus d ux plus e uy plus f u. Okay. So this PD is homogeneous if the right hand side of the PD is 0. Otherwise, it is homogeneous. Okay. And this PD is linear when it will be called as linear when I replace f of u plus u1 plus u2, that will lead to f of u1 plus f of u2. And if I multiply u with some constant a, means f of a multiplied by u, that will be equal to the constant multiplied by f of u. Then if these two conditions are satisfied, then my PD is called as linear. Otherwise, it will be non-linear. Okay. How we can find out by seeing the PDs whether it is linear or not? Then we see this A, B, C, D, E, F. Okay. If this A, B, C, D, E, F are either constant or function of only x and y, then this PD is a linear, otherwise non-linear. Okay. So suppose this is my PD in general form. So if this PD, suppose if this is a non-linear PD, then this can be termed as quasi-linear PD with respect to second order derivative if A, B, and C are either constant or function of x and y only. Okay. But this D, E, F are function of x, y, and u, ux, uy also. Okay. So then it is will call as quasi-linear. So here one important thing to note that PDs are very different from ODs. How? Generally, OD solution are possible, but the analytical solution of PDs are rarely possible. And in ODs, what we do, first we solve the OD, then we apply the initial condition and boundary condition to find out the exact solution. Okay. But here in PDs, the solution will depend on initial condition and boundary condition. And it is very sensitive to initial condition and boundary condition. Suppose we have a PDs, we have some initial condition and boundary condition. Then for this initial and boundary condition, the analytical solution may be possible. But if we change the sum of initial and boundary condition, that may be possible that its analytical solution do not exist, or finding of initial solution, finding of analytical solution is not possible. Okay. And generally this PDs contains a lines of discontinuities and lines of characteristics lines. Okay. So how we can classify these PDs? These can be classified as physically and in mathematical sense also. How we can classify the PDs based on physical problem? First type of PDs can be a marching problem. This can also be termed as evolution problem, propagation problem, or transient problem. The example can be del u upon del t equal to alpha Laplacian of u. This is nothing but a diffusion equation. Here u evolve or march in time and propagate in space. Okay. The main feature of this marching type of problem is that u at any time t equal to t naught will depend only on the time less than t naught, not time greater than t naught. Means what? The solution at any point will depend on its past, not on its future. Okay. Then other type of problem can be equilibrium type of problem. Okay. Equilibrium type of problem can be also said as steady state problem. So this is a typical example of a steady state problem. Laplacian of u equal to 0. So this Laplacian can be written in 3D. Del u upon del x square, del 2u upon del y square, del 2u upon del z square equal to 0. So here u at any location will depend on all other locations. Okay. Then third type of problem can be a eigenvalue problem. Means what? The problem will look like that. Laplacian of u will equal to lambda u with homogeneous boundary condition. Then this non-trivial solution for this type of equation will exist for some lambda, which will be the eigenvalue for this PDs. Okay. Similarly, physical waste problem, we can classify PDs based on its mathematical structures. So suppose we have a PD A uxx plus B uxy plus C uyy plus D ux plus E uy plus F u plus G equal to 0. Okay. We have this PD and we have some boundary conditions that are written here. So if I compute B square, which is a multiple of or a coefficient of uxy, okay, minus 4ac. This a is coefficient of uxx and this c is coefficient of uyy. Okay. If I compute this, if this comes to 0, then my PD will be parabolic partial differential equation. Okay. And if this comes greater than 0, then it is called as hyperbolic partial differential equation. These kind of PDs are usually observed in a marching type of problem. Okay. And if this v square minus 4ac comes less than 0, then this is elliptical type of partial differential equation. This type of problem, this type of PD is generally seen in equilibrium type of problem. Okay. So in general, this A, B, C can be a function of x, can be a function of x, y, t. In general, it can be a function of x, y, and t, which means what? Which means what? This b square minus 4ac may be changed in space and time. Means what? The nature of PDs may vary in time and space. Maybe in some region the PD will behave as elliptical problem. In some region it can behave as parabolic type of problem. Okay. Now discussing this, and let us see some physical problem, one physical problem, which is heat conduction equation. Okay, so we will not go into the derivation of the heat conduction problem. This can be derived using taking a arbitrary control volume and applying the first law of thermodynamics on the control volume. If you do that, you will find the energy in the control volume del E upon del T, the change in energy in the control volume, that will be equal to flux going out of control volume plus heat generation. Okay, so flux coming into the control volume and heat generation. Okay, so for solid, if we consider solid, the energy in the control volume can be represented as rho Ct, and this Q, that is flux, can be represented by Fourier law of heat conduction minus K grad of T. Then by putting these two values here, we find out the conduction equation. Okay. Now, if we consider the properties constant, this rho C can be taken outside of the time derivative, and this K can be taken out this divergence term. That will lead to rho C del T upon del T equal to K Laplacian of T plus Q triple prime. This is nothing but a heat conduction equation with constant property of material. Okay. So this Laplacian in 3D can be represented as this. So this equation is called as heat conduction equation, or in general diffusion equation. This alpha is nothing but the diffusivity. Okay. So if we consider the one-dimensional case, this Laplacian can be represented as del 2t upon del x square. So this equation will come. And suppose if we assume as no heat generation means what? This Q triple prime will go to 0, then it will lead to del T upon del T will be equal to alpha del 2t upon del x square. Okay. And if this is a steady state means what? T will not be a function of time. So this derivative will go to 0. In that case, will lead to del 2t upon del x square, sorry, d2t upon dx square will be equal to 0. Since t is only function of x, the partial derivative has been converted into total derivative. Okay. Now, let us consider an insulated rod, which is insulated from the periphery, and it is having some initial temperature T2, some temperature T2, and its boundaries are imposed temperature T1 at time t equal to 0. Okay, at time t equal to 0, we impose the boundaries as temperature T1. Okay, so this problem has governing equation this, since we haven't considered the heat generation part. So initial condition will be what? E at time equal to 0, and at every x temperature is what? T2, and boundary condition is what? At time greater than 0, at x equal to 0, temperature is T1, and time greater than 0, at x equal to L, temperature is T1. Okay. Now we try to non-dimensionalize this equation. Why we non-dimensionalize this? We non-dimensionalize this equation to reduce the number of parameters. Okay. So to non-dimensionalize, let us assume z equal to x by L and theta equal to t minus t2 here by t minus t1 minus t2. Okay. So from this, if we find dx, that will lead to L dz. Similarly, dt will be equal to t1 minus t2 d theta. Okay. Once we have found out this, we will put these two values in this equation. Okay. If we put that, so suppose if I am writing, so del T upon del T will be equal to what? T1 minus T2 d theta, sorry, del theta upon del T. Similarly, this del 2T upon del x square will be equal to T1 minus T2 divided by L square del 2 theta upon del x square. Okay. Now this value and this value we will put in this equation, and from both sides this and this will be get cancelled. So we will get del just a 1 minute. Yeah. So this will lead to this equation. Okay. Now here, if we incorporate this into this T, then it will be equal to del theta upon del tau, that will be equal to del 2 theta upon del z square. This tau equal to T alpha upon L square is known as Fourier number. Okay. Now what will be the boundary condition and initial condition? So if we put here at t equal to T1, these and this will be cancelled. So it will be equal to 1. So initial condition will be what? At tau equal to 0, at every z, theta will be equal to 1. Okay. And if we put here T2, then T2 minus T2 will be equal to 0. Means what? If tau is greater than 0 and z as equal to 0 and z at equal to 1, theta will be equal to what? Theta will be equal to 0. Okay. Fine. So this is what we have here. Okay. So this is my governing equation. This is my initial condition and this is my boundary condition. If you see this equation, this governing equation, this is nothing but a homogeneous partial differential equation, right? Okay. So this is homogeneous partial differential equation. And if we see the boundary conditions, boundary condition is also a homogeneous boundary condition. So if we have a homogeneous PDE with homogeneous boundary condition, then we can apply separation of variable method to solve the partial differential equation. So here what we assume theta will be equal to a multiple of some theta1, which will be a function of only tau, and theta2, which will be a function of only z. Okay. So if we take these two function multiple, that will lead to actual theta. Okay. If we use this separation of variable method and solve this problem, this is what we will get. This is the solution. Theta tau comma z will be equal to 4 upon pi summation of n will be odd 1, 3, 5 to infinite 1 upon n exponential of minus n square pi square tau multiplied by sine n pi z. In the dimension form, if I want to write, this will be equal to what? This will be equal to theta, you directly put value here. So t minus T2 divided by T1 minus T2, that will be equal to what? 4 by pi summation of n will be odd 1, 3 to infinite 1 upon n. You put the value of tau, so minus n square pi square alpha upon L square multiplied by t multiplied by sine n pi. You put z value x by L. So this is my analytical solution. So if you plot this analytical solution at different tau, you will get different profile of the temperature. Suppose at time tau equal to 0 means the initial time, at that time it will give me temperature will be 1 everywhere. Okay. And as we move in time, some part of will have temperature 0 to 1 then some part will have temperature 1. Okay, like that. So after some amount of time means what? If we find limit time tends to infinite, then this temperature will tends to T2 means what? My theta will tends to 0. So at a steady state, we will find something like that profile. Okay. Now this is the analytical solution. So what we do now, we will try to solve this problem numerically using the finite difference method. Then we will compare, since we know the analytical solution for this case, then we compare our numerical result with the analytical solution to have an idea what are the errors involved and how my numerical solution differs from the analytical solution. Okay. So let us start this 1D transient diffusion problem using explicit scheme. Okay. What do we mean by explicit scheme? Now we will discuss. So suppose we have some grids. So we have discussed this this x equal to 0 to L into into m+1 grid points. Okay. And we are assuming here uniform grid. Okay. So here also it is delta x, here also it is delta x. So this is my discretization in x direction. Okay. Similarly, I want to discretize this equation in the time. So this is my discretization in time. Okay. So suppose I want to find some value at here at ith grid point in space at time nth time. Okay. So what we'll use here, we will use forward in time and central in space scheme to find out this. Okay. So how we can use the finite difference method for this equation? We need to find out convert this differential equation into a difference equation. How we can convert? We will put del t upon del t and del 2t upon del x square using the finite difference formula. Okay. So this del t upon del t can be represented as in forward difference equation scheme ti at n+1 minus ti at nth time divided by delta t. Okay. And this del 2t upon del x square can be represented by using the central difference scheme as t at i-1 minus 2t I plus t at i+1 divided by delta x square. But these t I should write at what time? This is the question. This derivative that I am writing, at what time I should write it? So if we are using explicit scheme, we write this t at nth time. Okay. So we wish to find at n+1th time temperature. So we write the gradient at this derivative at nth time. Okay. So if we put now this value in the governing differential equation, so we'll get this ti at n+1th is n+1th time minus ti at nth time divided by delta t, that will be equal to alpha multiplied by the central difference scheme t at i-1 at nth time minus 2 ti at nth time plus ti+1 at nth time divided by delta x square. If I manipulate this equation, so I will get ti at nth+1 will be equal to ti at nth plus alpha delta t upon delta x square plus this value. Okay. So this nth at nth time, we already know the temperature value, means what? The RHS is what? Known, but LHS is unknown. So we can directly, we already know the value at initial condition, At initial condition, we already know the time, this temperature. So how our algorithm will go? We have the initial condition known. So at n equal to 0, Ti is known for every I means what? I equal to 1, 2, dot, 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 m. For every I, we know the temperature at n equal to 0. Now what we'll do? We will use this formula to find at n equal to, for this n equal to 0, we write this formula. So Ti at first will be equal to Ti at 0th plus alpha delta T upon delta x square, Ti minus 1 at 0th minus 2 Ti at 0th plus Ti plus 1 at 0th. These all values are known. Okay. So Ti can be found from this formula. Okay. Now we'll apply the boundary condition. So this will be applicable for what? I equal to 2 to m minus 1. Okay. So at I equal to 1 and I equal to m, we will apply the boundary condition to find the Ti at 0. Sorry, at 1. Okay. Now suppose we know the values at T1. Okay. So now we'll move for Ti2. Okay. So Ti2 will be equal to what? Ti1. Here also Ti1, Ti1, Ti1. These are all known. This also known. So we can find out. So like that we will proceed, and till this our desired time we'll find out the temperature. Okay. So this is what the explicit scheme. Okay. Now this explicit scheme, if we see that here, it is what? It is what? Truncation error is what? Order of delta t and delta x square. Means what? If I decrease the delta t and delta x, my solution will improve. Okay. So let us do one exercise. Suppose I have some delta x equal to 0.02. Okay. Then I solve by using the explicit scheme and plot the numerical results as these dots and analytical results at this line, that is blue line. Okay. And if I plot the derivative, I see the derivative is decreasing with respect to time. Okay. This is all right. Now what I want to do, I want to reduce the truncation error. So what I will do, I will decrease this delta x. Suppose I have decreased the delta x to 0.01. So what happened? This very bizarre kind of behavior takes place, and we see some these oscillations of solution close to the boundaries. Okay. So this is my analytical solution. This blue line, this red one is my what? Numerical solution. So close to the boundary, we see a large oscillations. Okay. Large oscillation. This large oscillation is what? Unphysical, and it comes due to the reduction in the grid size. Okay. And we also see the solution, the derivative, this derivative increases as we move forward in time. Okay. So this is a unphysical phenomena. So why this is happen? Now we'll discuss. So before going into that, let us discuss some of the important terminology that are important in the finite difference method. Okay. So first thing is convergence. So a numerical method is convergent if the numerical solution goes to analytical solution if this delta x and delta t goes to 0. So if I decrease the delta x and delta t, my solution will go to the analytical solution. Okay. So if this is satisfied, then this numerical method is called convergent. But this convergence criteria is difficult to show. Okay. Then second term is what? Consistency. So consistency is what? A numerical method is consistent if the truncation error goes to 0 as we decrease the grid. Okay. So it is called consistent if we decrease the grid size, the truncation error will goes to 0. Okay, this is what consistency means. Now the instability. Instability is what? A numerical method is stable if it does not allow random errors to grow in time. Okay, so any random error that is involved in the numerical calculation, if this random error does not grow in time, then the numerical method is called as stable, otherwise it is unstable. Okay, so generally this random errors comes from the round of error in the computer. Okay, so we have seen here this convergence is difficult to show. So here we come up with a theorem that is known as Lax equivalence theorem, which says that if we have a properly posed, if we have a properly posed linear partial differential equation, then the finite difference method is convergent if the method is consistent and if it is stable. Okay, so if we see this explicit scheme, it is order of what? Delta t and delta x square. Okay, so if I move this delta t to 0 and this delta x to 0, this order will moves to 0. Means what? Truncation error will truncation error will what? Truncation error will go to 0. Okay, means what? Means what? This explicit scheme is consistent. Okay, now we'll check the stability of this explicit scheme. Okay, so maybe due to that, this unphysical oscillation we see near the walls, near the boundary. Okay, so now we'll see that thing. Stability. Okay, so before going into that, let us see what we have. So we were solving. We were solving this ut equal to alpha uxx. It has some analytical solution equal to a. Okay, so now we are applying the numerical method explicit scheme. That will be equal to this expression ui at nth plus n plus 1th. That will be equal to ui plus alpha delta t upon delta x square in bracket ui minus 1 at nth minus 2 ui at nth plus ui plus 1 at nth. Okay, this is what we have. Now this gives me solution D if I do the solution in infinite precision machine. Means what? There is no round off error. If I do in that machine, infinite precision machine, then I got the solution D. And if I do in usual computer, means finite precision machine, I get the solution N. Okay, so the term analytical solution minus D, so this A minus D is called as delta, which is discretization error. Okay, so this is known as A minus D is known as discretization error. This discretization error will reduce as we reduce the grid size. Okay, so now the round off error will be defined as epsilon, that will be equal to n minus D. Okay, so generally this round off error are small and random, and it's decreases with the increase in the precision of the real number. Okay, now the numerical method is stable if epsilon do not or does not grow in time. Okay, otherwise it will be unstable. Now we do the stability analysis of this explicit scheme. Okay, so the explicit scheme, what the difference equation we got this difference equation, where r is equal to alpha delta t upon x square. Then this ui at n plus 1th will be equal to ui at nth plus r multiplied by ui minus 1 at nth minus u2 multiplied by ui at nth plus ui plus 1 at nth. Okay, so if I do this calculation in a infinite precision machine or a finite precision machine, what I will get? I will get some solution this of this u will be equal to ni at n plus 1th will be equal to NIS plus R, same term. Now, if the same calculation, if I do in infinite precision machine, I will get solution for U that will be equal to D. So simply I will replace this U with D. So this is what I will get. Di at n plus 1th will be equal to Di at nth plus R, Di minus 1 at nth minus 2 multiplied by Di at nth plus Di plus 1 at nth. Okay. Now I want to find out the round off error that will be equal to what? N minus D. Okay. So this will lead to the same equation, but D will be replaced with epsilon. Now the growth factor or amplification factor is defined as G. G is equal to epsilon at n plus 1th iteration divided by epsilon at nth iteration. Okay. So the scheme is set to be stable if this G, the growth factor, the modulus of growth factor is less than or equal to 1. Okay. We want it to be less than 1, but if it is equal to 1, then it is all right, since the error is not decreasing in time. Okay. So what equation we have? Ut equal to alpha u x x. Okay. So from here it will lead to t alpha epsilon x x. First we will put n, then we will put d, then we will take the difference. And for that we know the solution. The solution will look like that. The analytical solution, epsilon will be equal to summation at m am exponential of bmt exponential of j. J is what? J is under root minus 1 iota kmx. This is the analytical solution. Okay. So this, it has what? It is summation of m. So it has what? It has m number of modes. So now we'll take only one mode and do the analysis. Okay. So suppose I am considering some mode m. So this epsilon I can be represented like that. Now, if I want to write epsilon I plus minus 1 at nth, then this term will be same. This term will be same. But here this xi will be replaced with xi plus minus 1. Okay. Similarly, if I want to write this epsilon I at n plus 1th, so here t will be n plus 1th and this will remain same. Okay. Now I wish to find epsilon I plus minus 1 at nth divided by epsilon I at nth. Okay. This I want to find. So this will be equal to what? If you see this equation and this equation. Okay. So this term and this term is, if I divide, it will get cancelled. This term and this term will also get cancelled. Now I have this term in numerator and this term in denominator. Okay. So I have written this term exponential of j am x at I plus minus 1 divided by exponential of j km xi. So this xi can be represented as x plus minus delta x, and this can be represented as plus means what? Exponential. Then if it will go, if it will go in numerator, this term will go numerator, this term will get cancelled. So what I will get? I will get exponential plus minus j km delta x. Okay. So now in our equation, if you see, the g will be what? G will be 1 plus r, this epsilon I minus 1 at nth divided by epsilon I at nth minus 2 plus epsilon n I plus 1th divided by epsilon n at ith. Okay. Now you put their value here and here, we put the value. So it will be 1 plus r exponential of, so it will lead to the minus term. So it will exponential of minus j km delta x minus 2 plus this will be what? Plus exponential of j, here it is plus j km delta x. Okay. Now if you see, we can write e to the power I x plus e to the power minus I x, sorry, j x plus j kx by 2. This will be equal to cos of x. If we use this formula, so this will be equal to what? This will be equal to 2 cos beta, this term, and this term combination. This will be equal to 2 cos beta, where beta is what? Beta is what? J am delta x. Sorry, J will not be here. So this is what beta is. Okay. Now we can use this 1 minus cos beta equal to sine square beta by 2, 2 sine square beta by 2. Then we will get this expression. Okay. 1 minus 4 r sine square beta by 2. Okay. So stability condition says what? This growth factor, modulus of this growth factor or absolute value of the growth factor should be less than or equal to 1. Means what? My this 1 minus 4 r sine square beta by 2 should lie between -1 and +1. Okay. Now suppose we take this one, this 2. Okay. So 1 minus 4 r sine square beta by 2 is less than or equal to 1. This condition should be satisfied. Now this will lead to what? 4r sine square beta by 2 less than or equal to 0. This 4 is what? Positive. R is always positive. Sine square beta is always positive. So the multiplication of minus in my positive, that will lead to a negative term. So this negative term will be always less than 0. So this condition is always satisfied. Okay. Now the second condition, 1 minus 4 r sine square beta by 2 should be greater than or equal to -1. Okay. So now you do the manipulation. This -1 will come to this side, -2 minus 4 r sine square beta by 2. Now you multiply both sides by minus, then that will be lead to 2 divided by 4 r sine square beta by 2. This will be equal to r. So this is the expression that we will get. Okay. Now if we see this expression here, what it is saying, r should be less than some term. Okay. So if r is less than some term, so if this it is less than, if it is the less than the minimum term, then it will be less than for all other terms that are greater than RHS. Okay. So that's why we write, if this is satisfied, means what, for minimum RHS, if this condition is satisfied, other it will be already satisfied. That's why, means what, when it will be minimum, when this sine square beta by 2 will be maximum. So sine square beta by 2 will be maximum when it will be equal to 1. So you put simply here 1. That will lead to r should be less than or equal to 1 by 2. Okay. So r is what? Alpha delta t upon delta x square. So this condition, this will be what? 1 by 2. Okay. This condition should be satisfied. Okay. For the stability of the solution, means what? This solution is what? Conditionally stable. Means what? If this condition is satisfied, then only the explicit scheme will be stable, otherwise it will be unstable. So here what we were saying, what we have did, we have decreased the delta x without bothering about the delta t. So maybe in this case, r by 2 was coming greater than 1 by 2. That leads to the instability in the numerical solution. Okay. So we need to make sure while using the explicit scheme that this r should be less than or equal to 1 by 2. Okay. Whatever the procedure that we have used, it's called as von Neumann stability analysis or Fourier stability analysis. Here what we have did, we have found out summation of, there are n modes involved in the error, but we have considered only one error mode. Na? Then we have did the analysis. So this can be applicable only for the linear PDs only. In linear PD only we can write theta, if theta 1 plus theta 2 plus A1, theta 1 plus A2, theta 2 dot 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 is a solution, then theta 1 or theta 2 is also a solution of the PD. Okay. Now, all right, we have completed the explicit scheme. Okay. Now we will move towards the implicit scheme. So here also we will see the forward in time and central in space scheme. Okay. So here what we will do, this del t upon del t will write as a forward scheme. For the this space derivative del 2t upon del x square, we will write at n plus 1th in time. Okay. So this will be equal to what? Ti minus 1 at n plus 1th minus 2 multiplied by Ti at n plus 1th plus Ti plus 1 at n plus 1th divided by delta x square. If you do the manipulation, put in this equation, we will get equation r multiplied by Ti minus 1 at n plus 1th minus r plus 1 plus 2r Ti at n plus 1th plus r Ti plus 1 Ti plus 1 at n plus 1th, that will be equal to minus Ti at nth. Okay. So this is what? This is order of delta t in time and delta x square in space. Okay. This is nothing but a, if you see it clearly, it is nothing but a tridiagonal system at each time step. So we already discussed the tridiagonal system in last week. So by using the TDMA algorithm, Thomas algorithm, we can solve it at each time step. Okay. So how our algorithm will go? So for every I, we know at n equal to 0, Ti will be equal to T2. Okay. This is what initial condition. Now we'll put this n equal to 0 in this equation. Okay. When we put that, for I equal to 1, the boundary condition Ti at first will be equal to T1 and I equal to m. This Ti at 1 will be equal to T1. And for I equal to 2 to m minus 1, this will be what? This will be r multiplied by, you put here in this equation, you put n equal to 0. So Ti minus 1 at first minus 1 plus 2r, Ti at first plus r, here will be r. So here will be r multiplied by Ti plus 1 at first, that will be equal to minus Ti at 0th. This r is nothing but alpha delta t upon delta x square. Okay. So what we'll do to solve this equation, we will use TDMA to find t at first. Okay. Now similarly, at n equal to 1, if you do, so at I equal to 1, Ti will be equal to T1 from where? From boundary condition. Similarly, at I equal to m, Ti will be equal to T1 from boundary condition. Now from I equal to 2 to m minus 1, we will have r Ti minus 1 at second minus this at second minus r. Here will be also r. T at 2, that will be equal to. Again, we have a TDMA. Again, we have a tridiagonal system. So this can be solved using the Thomas algorithm. Okay, so this is what the implicit schemes. Okay. Now we can do the combined scheme, means what? We can use the explicit and implicit, the combination of both, as p multiplied by the del 2t upon del x square at nth plus q multiplied by del 2t upon del x square at n plus 1th station. So we have a choice of p and q such that p plus q equal to 1. So any combination of p and q we can take and come up to a combined scheme. Okay. Generally, the most common scheme, that combined scheme that is used, is known as Crank-Nicolson method. Okay. In Crank-Nicolson method, we take p equal to q equal to 1 by 2. So what we do here, this we write like this as earlier, and this we divide as alpha by 2 and alpha by 2. first central difference at nth time and second central difference at n+1th time. Then we do the manipulation, simple manipulation, and we get a difference equation. Okay, so this is what the difference equation we will get. If you do this and if you write the orders also using the Taylor series, so you will see that the order will not come in time as delta t. It will come as delta t square. Okay, so this will be what? Second order accurate in time and second order accurate in space also. So this is also the tridiagonal system. Here also one term, three terms are here, and this RHS is known. RHS is known. So this is also a tridiagonal system. So it can also be solved using the Thomas algorithm at each time step. Okay. We'll see one computer program where we will use the Crank-Nicolson method. To solve ED. Okay. So we'll see one problem. We'll make a computer program. Now, the stability analysis that we have seen for what case? We have seen for explicit scheme. Similarly, we can see for this implicit and Crank-Nicolson scheme. Okay. So if we go for this implicit scheme, this is what the difference equation. So this u will be replaced by, if I write the random error epsilon, this u will be replaced by epsilon. Okay. Now you use the same formula to get this. This is the expression. If I write am exponential of bm n plus t at m, here I should write at n plus 1 plus j km x at I plus minus 1. If you use that, if similarly you do for this epsilon I plus minus 1 at n plus 1th, that will lead to epsilon I at n plus 1th multiplied by exponential of plus minus j km delta x. And if you do like we have did for that, na, in explicit scheme we have did for that, na, n plus 1 will be equal to epsilon like that. So if you do that, you divide this into the LHS, then what we will get? We will get this expression. So this at n plus 1th, these two terms will come, and now we will combine this and these two terms. That will lead to 2r cos beta minus this will remain as same 1 plus 2r. Now if we divide by this here, so g will be equal to epsilon I at n plus 1 by epsilon I, that will be equal to 1 divided by 1 plus 2r minus 2r cos beta. Okay. So cos beta can change from -1 to 1. Okay. If we put -1, that will lead to -1 will be, we have -4, -2 will be what? Plus 2r. So it will be what? 1 upon 4r. Now this r is positive, so 1 upon 4r will be always less than 1, since r is greater than 1. Now if we take this cos beta equal to positive 1, if we put here 1, so this 2r and -2r will get cancelled, and this g will be equal to 1. Okay. Means what? This explicit scheme is what? This explicit scheme is what? This is unconditionally stable. Means what? It will be always stable. So we do not bother about the value of r. like that. No? In the implicit scheme, we have seen it is what conditionally stable. It will be stable only and only when R will be less than or equal to 1/2. Now for the similar case, similarly, we will see for Crank-Nicolson method. This is the difference equation. You take from LHS what common? N plus 1, I common in the LHS, and here you what take common? You take epsilon n common, and you put these two values there. So what you will get? You will get this expression for G. G will be equal to 1 minus R. 1 minus R, from here it will come 1 minus R, and this will combinedly give R cos beta. Okay, and from here you will get 1 plus R, and this term combinedly will give R cos beta. Okay, now this 1 minus cos beta you write into the sine square beta by 2 term, so then that will be lead to like this. How 1 plus cos beta by 2 will be equal to sine square beta by 2. Okay, this is the formula that we are using. This is the formula we are using. Okay, so this is what the expression we have got. Now if you see that this R sine square beta by 2 will be always positive. Okay, so I am subtracting some positive number in 1, and then the same positive number I am adding in 1 and then dividing it. So this term will be always less than this. Okay, means what? Means what? G will be always less than or equal to 1. Modulus of G will be always less than or equal to 1. Means what? Similar to the implicit scheme, this Crank-Nicolson scheme is also unconditionally stable. So what we have, sine square beta by 2 na, is greater than equal to 0. Okay, so the minus will be what? So I can write as minus R sine square beta by 2 will be always less than 0. Huh? Now we add, multiply both sides by 2. Okay, so this can be said. Now you add 1 in both sides. Okay, add 1 in both sides. So this term will be what? Less than 1, and this term is what? Greater than 1. So if you divide that, some number that is some number that is this number, some a number that is less than 1, and some number b that is greater than 1, if you divide that, this will always lead to number that will be what? Less than 1. Okay, so this is what has been covered in week 8. Okay, now we'll see some problems. Okay, we'll solve some problem. So suppose we have this equation, del 2t del u upon del t will be equal to del 2 upon del x square. So I need to find out whether this equation is linear or non-linear, parabolic, hyperbolic, or elliptic. So what is this type of equation? By seeing here, you can say that a is what? A is what? 1. B is what? 0. C is 0. And other terms also are 0, na? D, E, F. These are also 0. Means what? This is what? Constant or a function of x and y. Means what? It is what? If I change the color, it is what? It is linear. And how we check the parabolic and all? So b square minus 4ac. So 0 minus 0, that will be equal to 0. So it is what? This is parabolic and it is linear. Okay. This equation, this is also a linear equation. And if I expand this equation, del 2 u, that will be equal to del 2 u upon del x square plus del 2 u upon del y square will be equal to 0. So here a is equal to 1, b equal to 0, c equal to 1. So b square minus 4ac, that will lead to minus 4. Means what? My negative. Means what? This equation is what? This equation is what? Elliptic and linear. Okay. Now we have this problem, del 2 u upon del u upon del t will be equal to del 2 u upon del t del x square. Sorry, it will be x. We have this equation. So now we need to see this equation is what? Time marching equilibrium problem or eigenvalue problem. We know that this is a time marching problem. Now this problem is called as transient heat conduction problem. Okay. Now next problem, this del 2 u upon del t equal to u del 2 u upon del x square is described as this expression in explicit scheme. Okay, this is explicit scheme. So then I need to find out the value of k. So in explicit scheme, k is what? K is nth n. So what will the truncation error? We know this will have a truncation error of delta t and delta x square. Okay. Similarly, if I go for Crank-Nicolson scheme, then in that case, my truncation error will be second order in time and second order in space. Okay. Now the next problem is what? We need to comment on the stability of explicit scheme, implicit scheme, and Crank-Nicolson scheme. We note what? This is what? This will be stable only when R is less than or equal to 1 by 2. Means what? It is conditionally stable. This is what? This is always stable, means was unconditionally stable. Similarly, this is also unconditionally stable. Okay. So this is what assignment problem. Now we'll see one practice problem. This is the practice problem. Okay. So the practice problem is like that. We need to write a computer program to solve the PD up to what? Up to steady state. Okay. Using Crank-Nicolson method. What is the PD? PD is del u upon del t equal to del 2 u upon del x square, like we have seen in whole lecture. What is the initial condition? Initial condition is u at t is equal to 0 is 1. And u, what is the boundary condition? U at x equal to 0 and x equal to 1 is 0 for time t greater than 0. Okay. We need to take this delta x as 0.01. Okay. Delta t will take as convenient to us, since this is a unconditionally stable. So we can take large delta t also, but that will lead to some truncation error. Okay. Now we need to solve this, write a computer program, and we need to plot the result. Okay. Fine. So now I will stop share from my iPad and share the screen from the computer. to write the program. Okay, so how we can do that? First, I need to write the difference equation for this. Then that difference equation I will solve using the TDMM. Okay, so this is the expression we have. Okay, so this time derivative can be written as forward in time u at n plus 1 minus ui at nth ui at nth, that will be equal to 1 by 2 central difference at n plus 1 plus 1 by 2 central difference at nth, since we are using Crank-Nicolson method. Okay, if I assume r equal to delta t upon delta x square, then this equation will lead to this r by 2 ui minus 1 at n plus 1 plus minus 1 plus r ui at n plus 1 plus r by 2 ui plus 1 at n plus 1th, and this in RHS we will have minus r by 2 ui minus 1 at nth minus 1 minus r ui at nth minus r by 2 ui plus 1th ui plus 1 at nth. Okay, so this is what this is diagonal system. Okay, this is diagonal system. So this can be solved using the Thomas algorithm. So what we'll do, for I equal to 2 to m minus 1, we'll define a equal to r by 2, b will be equal to what, this value, and c will be what, this value. So I am not now what I am trying to do, I am trying to write as a TDMA, diagonal system, u I minus 1 at n plus 1th plus b ui at n plus 1th plus c ui plus 1 at n plus 1th will be equal to some di. Okay, this is what I am trying to write now. Now we know for I equal to 1, u I n plus 1 is 0, and for that case what will be a will be 0, b will be 1, c will be 0, and d will be what, 1. Okay, similarly at I equal to m, ui will be what, 0, that means what, a will be 0, b will be 1, c will be 0, and d will be 1. Okay, now what we'll do, we will use the TDMA at each time step. Okay, so suppose at n equal to 0, ei is equal to 1 for all I. Okay, and for I equal to for other cases, so if we use this value, so this 0 will be replicated here in D. Okay, and if you write that, then we will get this kind of system of linear equation. Okay, so first equation will 1 0 0, that will be u1, this is at 1, this is at 1, this is at 1, this is at 1. Okay, so when I am putting n equal to 0, so for first case d will be 1, last case d will be 1, otherwise it will be d, and this d will be function of u0 I, u0 I minus 1, and u0 I plus 1. This will be function of like that. Okay, now in this TDMA, if I do the forward elimination, then by bi will be what, bi will be what, bi minus ci ai upon bi minus 1. If you do not remember this, please revise the week 7, there has been discussed the Thomas algorithm. Similarly, di will be what, new di will be di old minus di multiplied by ai divided by bi minus 1. Okay, then we will do back substitution. In back substitution, equation n will be equal to xn, or here it will be un, um will be equal to dm divided by bm. Okay, and other will be what, if I write xn minus 1, that will be dn minus 1 minus cn minus 1 xn divided by bn. So in generalized sense, this can be written as, okay. So now we'll use this Thomas algorithm to solve this problem, okay. So now let me share the screen from my computer. I hope you are able to see my screen. Fine. So just give me 1 second. So first what we will do, we will do the discretization. First I will just clear everything that I have. Clear. I will do the clear all. Then what is my delta x here? So delta x, suppose I am writing as h. So h is what here? 0.01. It is given in the question. Okay. Now h is what? This. So what will be my number of grid point? Nx will be what? I have upper limit 1, lower limit 0 divided by h. Okay. So let me just check is everything is going all right or not. So this is what my nx. So my point will be what? So this is what? This is number of interval. If I do +1, then this will be equal to number of grid point. So total length divided by the step size, that will give the number of interval. If I do +1, then it will give number of grid points. Okay. And this is what? This is delta x. Now I have found out the delta x. Okay. Now delta x I have found out. Now I need to do the discretization. So let us do the discretization. So discretization I need to do. So for I equal to 1 to nx, some x will be equal to what? X of I will be equal to x of I minus 1 plus h. Okay. Now I need to define first this. So x is what? X is zeros of, initially x is zeros of nx comma 1. Okay. Now let us see whether it is. So if we go from I. So now So now if I see, this is my x. So 0, then 0.01, 0.02. So we have created a grid in x with a step size 0.01. Now the grid has been defined. Now what we need to do? We need to define R. So R is what? Delta T upon delta x square. R is delta T upon delta x square here. So let delta, sorry, dt, suppose I'm writing. So let dt is equal to 0.001. Okay. This is what I am taking as dt. So time step size. Okay. Now what I will do? Now I will define R equal to what? R is what? dt divided by h square, h multiplied by h. So this is my R. Okay. So this is my R. Now what I will do? Now I will define u old. U old will be equal to what? Initially the values are ones. So ones of nx comma 1 size. So my initial value is 1. So I have defined as the old equal to ones. Okay. So if I see here, see it is now 1. All the values are. Now I am defining the new value u new equal to, initially I am assigning as zeros of nx comma 1. Okay. This is what I am doing. Now in the problem it has been written that I need to solve the problem. I need to solve the partial differential equation up to steady state. Okay. So steady state means what? Steady state means what? The solution will not change with time. Means what? That the solution at suppose at time equal to n, it is converged. It is not changing. Okay. So at that time, the solution at time n minus 1 will be almost equal to at solution time at n. Okay. So I am defining some epsilon. This is what? This is my user defined value. Is epsilon equal to suppose 0.001. This is what I am taking. If my solution is the maximum difference between the at any interval, at any n plus 1 and nth stage of time, if this is less than this, then I will assume that my solution is converged. Okay. And I am defining this maximum error, some max error equal to some, I'm assigning it as suppose 1000 earlier. So what I will do, while my maximum error is greater than epsilon, I will do the, I will calculate. Okay. Now, so now what we need to do? First, we need to define this variables a, this variable a, b, c, d. So what will be the value of a? So initially a is zeros of, suppose I am saying zeros of nx comma 1. Okay. This is my a. Similarly, this is my b, this is my c, this is my d. Okay. Now what is the value of a at 1? A1 is what? At I equal to 1, we know that u1 is equal to 0. u1 equal to 0 means what? u1 equal to 0 means what? Means let me share my screen from the iPad. Okay. At I equal to 1, my a is 0, here a is 0. Okay. Similarly, at I equal to m, or the maximum value at the last grid point, my a is 0. Similarly, c is 0, b is 1. So I will do what? I will just put these values, okay, on the expression, and these values for I equal to 2 to m minus 1. Okay, this is what I am going to do now. Okay, so keep in mind, a1 will be equal to what? a1 will be equal to 0. Similarly, b1 will be equal to what? 1. c1 will be equal to what? Will be equal to 0. And d equal to 0. Okay, this is we have defined. Now similarly, at last grid point we need to define. Control C. So nx now what I will do, for suppose I goes from 2 to nx minus 1, my a of I will be what? A of I will be what? This will be r by 2. Okay. Similarly, b of I will be what? B of I will be minus of 1 plus r. Okay. Similarly, c of I will be what? C of I will be equal to what? R by 2. So I have defined A, B, C. Now I need to define D. Okay. To define D, I need to know the value of U. So why I'm doing U new 0? Because in every state iteration will start new as 0. Okay. So now I need to define the D. So D will be what? D of I will be what? D of I will be what? Minus R by 2 multiplied by u old of what? I minus 1. Okay, minus in bracket 1 minus r multiplied by u old in bracket I. Okay, minus r by 2 multiplied by u old in bracket u old in bracket what? I plus 1. Okay, so this will be what? This will be my di. Now I have defined a, b, c, d, all I have defined. Now I need to do the TDMA. Like TDMA. You can make the separate function for TDMA, but I am doing here only. So in TDMA, what we do? We will go from for I equal to 2 to nx minus 1. Here what we will do? First we will define some t. T will be equal to what? This pivot point a I divided by b I minus 1. Okay, so this is my t. Now my d new b will be what? New b of I will be what? New bi will be equal to bi minus ci multiplied by this t. Okay, similarly my di will be what? So di will be what? Di minus this. Now this is what? Forward elimination. This is forward elimination. Okay, now what I will do? I will do backward substitution. In backward substitution, what will be my xn means what? So my u new of nx minus 1, that will be equal to b of nx minus 1 divided by b of nx minus 1 from TDMA. So nx minus 1 I have got. Now I will go for I equal to nx minus 2 in minus 1 step. I will go up to 2. What I will write here? U new u new will be equal to what? U new of I will be equal to b of I minus c of I minus 1 minus 1 multiplied by u Whole divided by what? Okay, this is the formula. Now I have done the forward elimination and backward substitution. Now I need to apply the boundary condition also now. So boundary condition is what? U mu at 1, that will be equal to what? 0. At nx, that will be equal to what? 0. So we have solved this now. Now just we need to plot this. So let me save this first. Suppose I am saving it at the desktop. Why it is taking so much time? Okay, so I haven't put the condition. So let me put the condition while this. Then here what will be? Then after doing all the things, what I will do? My old will be what? Old will be what? U of new. And before doing that, I need to find out the maximum error. So max error, that will be equal to the maximum of absolute of u new minus u old. Okay, so this will this will be my maximum error. Now if I run this, so it has run now. So just to indicate that how many iterations it has gone, I will start with some j. Suppose I am defining some j equal to 1 here. And once one while loop is completed, I will do j equal to j plus 1. Okay. Now if I run this, so it has converged into a 13,000 iterations. Okay. Decrease of silent percent. Now let us do the plotting. So now we'll do the plotting. So I will just copy from here. There I have written it. It means there is some problem in the code. Okay. So I need to modify that. So I need to see where I am making some mistake. Oh, This is all right. This is all right. This is all right. This is all right. This is also correct. Okay, so if I am writing here, so here it will be what? In the back substitution, I have made the mistake. So here is what? Xi equal to di minus ci, di minus ci multiplied by xi plus 1 divided by bi. So I have written what? Di minus ci, this will be ci, this will be what? This will be I plus 1, this will be I plus 1, and this will be bi. Okay. So I will be what? This. Now I think it will give us the right result. There is still some mistake. Okay. So I have made this code also. So let me check here. This okay, this will be d not di, this will be di minus 1. So in TDMA, this will be di minus 1. There it will come from di minus 1. Okay. Now it will go here. See, it is giving the right result. So I need to increase the error silent value. Suppose I have increased it. So still it hasn't got to the steady state, so I need to increase it more. Now if I run it, see, at t is equal to 487th iteration, it has gone to a steady state solution. So this is my numerical solution at different time step. Okay. Now you need to what you need to do? You need to do now you need to plot the analytical solution also on this point. Rather than plotting it as a continuous, if you plot it as this numerical plot, this numerical result as a scatter plot, and this line plot you plot as the analytical solution. Okay. And you see what is the is it matching or not with the actual result. Okay. I hope this is clear now. Suppose I decrease the delta t. Now delta t is what? Delta t, where is delta t? I decrease the delta t with one more zero. Now if I run, it started from this blue over here, green one. Now see, now it is starting with more like that. Na? Earlier it was like that. Earlier it was like that at t is equal to 50, and it was like that at t equal to 10. Now it is more towards that. So now if I change the time step here, where is the time step? So here, suppose here I am putting it now. Suppose 200, and here at 150, 1500. Now if I run it again, but I do not change the ligand. So I need to change the ligand. So this is what at t is equal to 200. No, at t equal to 200 and t equal to 1500. This is what we will get now. Okay. I hope you all would have understood this. See, here I have made the mistake. Here I have written TDI. That's why the solution was not converging. So it is I minus 1. Here it is I minus 1. Okay. In this expression. So this is what we need to discuss in this week 8. Okay. First, what we have did, we have seen what is homogeneous PD, what is linear PD. Then on the basis of mathematical structure, what is parabolic PDs, what is hyperbolic PD, and what is elliptic PD. Then physical problem based, what is time marching problem, what is equilibrium problem, what is eigenvalue problem, that we have seen. Then as we have seen one practical problem, that is cooling or heating of insulated rod. Okay, that we have solved analytically. We have not done the whole derivation, but we have seen its analytical solution. Okay, once we have seen its analytical solution, then we have moved toward the numerical solution. There we have seen three methods. First is explicit scheme. Then we have seen implicit. Then Crank-Nicolson scheme. So also we have seen the stability that is involved with all these three methods. We have seen that the explicit method is conditionally stable, while the Crank-Nicolson and implicit method are unconditionally stable. This von Neumann or the Fourier stability analysis we have used that are applicable for the linear PDs. Okay, on that, suppose we have find out the error as a summation of n number of mode, then we can take one mode and do the analysis on that. On the basis of the analysis, we can say whether the numerical scheme is stable or unstable. Okay, fine, clear. Then we have also solved some of the problems. These are some easy problem. Then we have seen the one computer problem where we have made a computer program for this. Del u upon del t will be equal to is this partial differential equation with the given boundary condition. Okay. So this is all for the week 8 problem solving session. Now I am stopping the recording. Thank you. Thank you. We'll meet again next week, Sunday at 3 to 5. Okay. For week 8. Thank you so much.